So this is the point. HIV from definition, we will not go into definitions of the syllabus. We will simply tell you the meaning of the word HIV, that is human immunodeficiency virus. So from that word, it is just a virus. Okay, it's just a virus named human immunodeficiency. And the reason why it's named human immunodeficiency, the word is immunodeficiency. Immuno for immunity, deficiency for lowering. So basically it attacks your army that is supposed to protect you from diseases. So it kills your CD4 cells. It doesn't actually what it does, it gets into the CD4 and then uses the machinery or the mechanisms of the CD4 cells to make its own, to survive, to make its own DNA and its own proteins, and then to also multiply. So on its own, a question that has always been asked every single day, is HIV as a virus dangerous? Does it live? Is it a living thing? Are viruses living things or are they not living things? And the reality is viruses cannot survive on their own. They have to get into the cell, and once they are into the cell, they can now start to multiply using the cellular machinery or mechanisms to make their own. This is one reason why it's difficult to target viral conditions. Like, for example, all of us have a flu. It just subsides because your immunity is super. So, for you to control viral conditions, the first thing you have to do is you have to make sure that your immune system is super. And we'll talk about how to boost the immune system. And this will actually be helpful to our patients who are HIV positive, because we focus so much on talking about the medications and the drugs, but we fail to talk about the dietary modifications, the exercises, the sleep patterns, stress levels, to just make sure that your immunity is super high so that it can actually help you suppress the viral multiplication and therefore the viral load. Now remember this. The reason why people take antiretroviral drugs, ARVs, is because they first want to lower the viral multiplication. Remember, this virus is multiplying. So you want to lower the viral multiplication, and then your immunity takes over. This is where we forget. We think that the drugs will come and lower our viral multiplication, and that is it. And now we heal, or now we are good to go. No. The ideal situation is just like antibiotics work. They come in to lower the viral burden or the bacterial burden to a certain level that your immune system can take over. And this is what we need to talk about. We need to talk about how to boost this immunity so that it can actually take over without needing an assistance from medication all the time. Okay? So antibiotics lower bacterial load to a certain level and then your immunity takes over. This is the same thing concept that is happening here. Antivirals and antiretrovirals actually suppress the viral level or the burden to a certain level so that your system can take over. Okay? Now, HIV is very tricky. Just like any other virus. On its own, no harm. But when it gets into the cell, gets contact with the cell, it actually gets into the white blood cells and uses the mechanisms of the white blood cells to make sure that it survives. Okay? So when that happens, it becomes difficult for you to target it, because if it's inside your white blood cells, that means if you target the virus, you must target the cell, which will be your immune cells. So you'll have to clear your immune cells as a result of that. But I want you to understand this. We take HIV medication because, number one, we want to lower the viral load, again, so that your immunity takes over. And number two, we want to lower this viral load to an extent, a very lower level, very lower, that we cannot detect it on a viral detection test. Misconception number one is already coming in here. When you go for that viral load test, and then you're told your viral load is undetectable, so it is below a certain level that cannot be detected in blood, that does not mean you will turn HIV negative. No. It means if you test for HIV, you still have the antigen of HIV in your system, in your blood. So you will still turn HIV positive. But your viral load is very low that it cannot be detected in blood, and therefore you cannot spread. So number two reason why people take antiretroviral drugs is because they want to lower their viral load to a certain level that they cannot spread it. So we want to prevent the spread of HIV. Okay? So we reduce viral multiplication and viral load, and then we reduce the spread. And through that, we prevent total spreading of HIV and infecting and affecting other people. That is what we are supposed to do. So you don't take the antiretrovirals to get healing, because there is a study that is actually, I actually, when I was doing research on this, I read a certain study that was talking about the first drug that was discovered for HIV, and that drug is what we call AZT. Now, if you've had an interaction with these medicines, you know they are labeled using codes, and those codes are basically the chemical names. So the chemical name is very long, but they use basically short forms. Like AZT is supposed to mean is a short form for the drug that is called zidovudine. That drug is being used until now. Now there was an interesting story about this, because this was the first drug to be used to manage or lower the viral load in HIV patients. And this was about 1964 or 1980s. No, 1964, it's when it was actually detected to have an antiviral activity. So this drug was actually being tested for anti-cancer activity. Underline that. So in 1964, it was tested for anti-cancer activity in mice, but it wasn't effective the way they wanted. The side effects were immense, so it didn't even qualify for the clinical trials. So they just tried it in mice, the preclinicals, and then now after that they put it on the shelves. And amazingly, when HIV was becoming a pandemic, just like COVID in the 80s, what they did is there was a company in UK. That company is the one that actually was at that moment in time producing antiviral drugs. So this company thought, hey, there's a drug that has been left on the shelves for quite some time. Why don't we use it and try out, possibly do some tests and some trials here and see if it can actually suppress this virus? Because when HIV was actually new, I'll put new in quotes, it was like COVID. People were so afraid. It was so advertised in the media. Everybody was afraid about it. And even though they say it only killed a few thousands of people, everybody was scared of this. The pictures that were being put in the media of people who are thin were actually tremendous. And people were just wondering, oh, if I get this one, I'm gone. Is this me? If I'm tested positive for this. And remember that time, the tests were not even adequate to prove that this was actually HIV. So they went clear to this drug on the shelf that is called the zidovudine, and they took it and started clinical trials. Unfortunately, they did not finish the clinical trials because of the pressure that was coming from the people. Just the same way, when you went into that supermarket during the COVID season, you did not find a hand sanitizer. Why? Because there was pressure that was coming in from the public that they need more sanitizers, and everybody's in the supermarket with trolleys carrying all the sanitizers on the shelves because we were so scared. Now, that is the role of the media, to just sell you the fears, okay? So, on this one is a different story. At this moment in time, there was no media such, but there was mainstream media, which was actually controlling most of the things. So now, this is what happened. So they took this drug, took it for clinical trials, but the pressure that was coming in as a result of the public and public health officials, they actually pushed the Food and Drug Administration of the United States to approve this drug after 20 months, of trials. Now remember, it had not attained the full trial period, because at that moment in time, there was no so much advancement in technology, and drug approval was taking about 8 to 10 years to just approve one drug for one condition. But now comes this drug that has been on the shelves and is actually approved within 20 months. Question marks. The COVID vaccine was approved within 8 months. Question marks. The drug discovery process takes about 8 to 15 years for you to come out with a new drug and a new agent. So there is no way a drug can come out within 8 months and it is effective. Okay? So sink that in. That was the first drug, and apparently that drug is still in use up to now. It is actually part of the therapy that is supposed to prevent mother-to-child transmission. It's called zidovudine, AZT. So you can check it out. Okay? So that aside, let's talk about the HIV life cycle, because through talking about the life cycle, that's where we'll get to know where do these drugs target and what are the mode of actions of these drugs. So when we have the mode of action of these drugs, we'll actually help pharmacy students here. We'll actually help nursing students, the medical students who are on board, and even the laboratory students, laboratory technology students who are here who carry out these tests. So you'll have a rough idea of this. Now, on this paper, I have actually drawn something that is very important. Now, this is actually a virus, the HIV virus for that matter. And I know most of you have interacted with this before. So this is the HIV virus. Okay? Now I hope everybody is seeing this clearly. So let's take you through. So one, you should know that the outer covering, the one that is in red, that is an envelope. That's what we call the envelope. Okay? So a virus is enclosed into an envelope. Remember that a virus is a non-living thing. So it's just a simple DNA, which is actually non-living, plus some few materials here and there, some enzymes here and there, and then it's enclosed into a protein covering. And this is the envelope, which is basically a protein covering. And then inside it, we have things that look like coils. If you see those things that look like coils, that is what we call the mRNA or the DNA. This is the genetic material. And if you look closely, we have something else that is surrounding that material. It's called a capsid. Do not struggle to understand these things. Do not struggle to cram. Simply understand that this is a virus and it has mRNA inside, the viral RNA, and then it have two things. We have the blue stuff and the red stuff, those dots. Those two dots are actually the enzymes. And we'll get to realize where these enzymes work as we continue with this live. So this is the reality. You see that's a virus, and on the surface of the virus, we have these things that look like spikes. These things that look like spikes are what we call the what? They're actually called the glycoproteins. And what they do is they help the virus to attach to cells. So you realize that these are actually the receptors, what we call the receptors. So what do receptors do? Receptors help this virus to identify that this is the cell that I'm supposed to be attached to, and then we attach that cell, and then the process now begins. So understand this. For this virus to attach to that cell, that CD4 cell, the white blood cell, it must have these receptors. And these receptors, one of the most important receptors for these viruses is what we call the CCR5 receptor. Do not cram it. That receptor, I'm telling you about that CCR5 receptor because the first drug to prevent HIV or the first drug to protect you from HIV is actually going to block the virus from attaching to the cell by blocking that receptor called CCR5. So when this virus comes into contact with the cell, if you block the attachment of the cell to the virus will not enter into the cell. That is step number one. So as we talk about the life cycle of the virus, you'll realize that number one is binding and attachment. So the virus has to attach to the cell through these receptors, and one of those receptors is what we call the CCR5. I want you to understand that on CCR5, we have a drug that is called Maraviroc. So Maraviroc is a medicine that actually blocks the virus from attaching to the cell. So it blocks these receptors of the virus from attaching to the cell. Now that Maraviroc drug is coming from a company that we all know, it is called Pfizer. Okay, so Pfizer makes this one. And then after the virus has attached to the cell, now it's time for it to enter into the cell. So you attach, that is binding and attachment, and then now it has to enter into the cell. But before it enters into the cell, it has to fuse its envelope. So the envelope has to fuse with the cell membrane of these cells, the white blood cells. Okay, so this envelope now attaches and fuses with the white blood cells cell membrane, and that is what we call stage number 2, which is actually called the fusion. And on fusion, we also have a drug that blocks the virus from fusing with the cell membrane of the cells. Those are what we call the fusion inhibitors. Fusion inhibitors, they inhibit fusion. One of those drugs, and actually the most common one, is what we call the enfuvirtide. Don't struggle to understand them. Don't struggle to cram them. Simply get the concept. We have to attach, we have to fuse, and then once we fuse, we have to enter the cell, because through fusion, the cell allows the virus inside. Now, as the virus comes inside the cell, it gets into the fluid that is around the organelles and stuff, okay? But the target of this virus is to get into the nucleus so that it gets to form, to use the DNA of the cell to form its own DNA and its protein at the end of the process. So those two dots that you saw, this red one is what we call the reverse transcriptase. When you hear the word S at the end, the word transcriptase, isomerase, ASE at the end, is basically an enzyme. So those two dots, remember I told you, are enzymes. So enzyme number 1 is reverse transcriptase. actually help this virus to transcribe its mRNA to DNA. Now, transcription. And then DNA to the proteins is what we call translation. I'm taking you back to biology, basic biology. Or those of you who have gone to a medical school, I'm taking you to basic genetics. mRNA to DNA, that is transcription. DNA to proteins, that is translation. So now remember that enzyme is called reverse transcriptase. Okay? Reverse transcriptase. So actually, it is the one that activates the virus to transcribe its mRNA into DNA. We are on the process of making viral protein. So it is now inside the cell. Now its enzymes are being released. The virus releases that reverse transcriptase. It helps it to make its own DNA. Understand that, okay? That's the basic one. Now, this DNA will now fuse into the nucleus of the cell, your white blood cell. When it gets into the nucleus, remember in the nucleus is where you have the DNA of your white blood cell. Okay? So the reason why this enzyme is actually produced is to make sure that this virus forms the DNA that will help it get into the nucleus so that it gets to the DNA of your cells, the white blood cells. Take some glass of water and just relax on that one before we continue. Now, at this level, we have drugs that are called reverse transcriptase inhibitors. So their role is to inhibit reverse transcriptase, to just block that enzyme from actually making more viral DNA from the mRNA. So at this moment in time is where we have most of the drugs that you people know. Most of the drugs that are used for PEP, most of the drugs that are used for PrEP, most of the drugs that are combined to form that antiretroviral therapy are actually in this group. The reverse transcriptase inhibitors. They inhibit that viral enzyme called reverse transcriptase. Number one on the list is actually tenofovir. Very important first-line medication is called tenofovir. Now, I'm going slow by slow because I'm telling you about the life cycle and again giving you drugs and where they work. So I'm also giving you the mode of action of these drugs. So we will use that to question the same life cycle and the same medication. So be very keen. Okay? Be very keen. So number two drug on this is actually called efavirenz, a very normal drug for people who have HIV, another combination. We also have nevirapine. And I know if you've been here, if you've had a chance to read about HIV, you know the names that I'm mentioning. We also have the most common drug that is literally actually is considered safe even in children, is called lamivudine. It's actually also used in hepatitis. So if you've ever had a chance to get hepatitis, you will actually have tenofovir plus lamivudine. That is TDF stroke 3TC. Don't struggle to understand or cram that. And then we have the AZT. Remember the drug that we said was the number one drug to be used in HIV in 1980? That is the zidovudine, the AZT, the one that is questionable, the one that there was no conclusive evidence that it suppresses viral load, but it still was approved by FDA. That one, zidovudine. And then one drug that is present in your pre-exposure prophylaxis. When you want to prevent yourself from getting HIV, but you want to have sex with a partner who is HIV, this is for the concordant couples, okay? The concordant couples, the one that one is positive, the other one is negative. This drug is actually present in PrEP. It's called the emtricitabine. There are people who already have used PrEP before and they understand. They have read that. Emtricitabine. So most of the drugs for HIV are coming from this group. Because remember, we have to combine drugs. Again, they used to make one drug to target the virus, but they realized the virus mutates so fast. So now they had to target different places on the life cycle. And from the beginning, they have a drug. If you just realize, from the beginning of the cycle, they have a drug that blocks every place. But they have never found a medication to treat HIV, even though they have drugs that block the virus from getting in contact with the cell, that blocks the virus from fusing with the cell membrane, that blocks the virus from producing that reverse transcriptase that will actually help the virus to make the viral proteins and DNA. They even have a drug that will actually inhibit replication. Now remember, when this viral DNA now gets into the nucleus, it has to use the DNA of the cell to actually make its own DNA and make longer chains of DNA. That is what we call the replication stage, and that is stage number 4. Are you following? Yeah, discordant, sorry. I said concordant, sorry. This is Min O'Brien. Thank you so much for that correction. It's discordant couples. Thank you so for that correction. I appreciate. Good. So we have a drug that is supposed to prevent attachment, fusing, replication, and even assembly of the proteins. Now, after the virus has formed its proteins, the longer chain proteins in the nucleus, these proteins, the viral DNA and also the cell DNA, they have to actually be assembled together and then form a coat around them so that they actually become something that can get out of the cell and be dependent on itself. Now, this accumulation or this assembly is actually another stage, because once they assemble, they move near the cell membrane. And when they move near the cell membrane, they are preparing to get out of that cell. But remember, they have conquered this cell. So this cell is not active anymore. They have conquered it. Once they conquer that cell, they are good to go. Now they can leave the cell and go and invade other cells. Okay? So that is the assembly stage. And the weird part is, this other enzyme that we did not touch, the blue one, is one enzyme that actually prevents the assembly of this viral DNA and the genetic material that has been fused with your own. Now, that enzyme is called protease. So there is a drug that is called atazanavir, those that end with VIR. Atazanavir is actually one drug that is also used as PEP. So it's part of the regimen that is used as post-exposure prophylaxis. That is the PEP. Okay, so after you've had sex and you realize there's a chance that I could have contracted HIV, you run to the hospital and then you are given drugs that are supposed to prevent you from getting the HIV infection.